Good afternoon. This is Kevin Bates, and I'm talking about the exploratory analysis and machine learning of county-level home prices and economic factors in the United States. This is my spring capstone for Data 670 at the University of Maryland University College, or global campus. So the background of the project is that affordable housing is a very hot topic throughout the country, and better understanding of the link between median home prices and economic indicators can give better insights for individuals who are looking for affordable housing, companies that are looking for affordable housing, or governments that are looking to expand their influence or maybe align their policies with how they want their county to grow in the future. And personally, I'm interested in house prices because I don't want to live in Southeast Texas forever. So where else can I live in the United States? The project scope is that I gathered four main data sources. I got the primary data set, which is the Zillow Home Value Index at a county level, and I used the dates from 2010 to 2017. These are monthly values that are calculated by Zillow and published. They do extend farther back, but the further back you go, the more sparse the data becomes. As the data sets evolved, additional counties have been added into it. With that primary data set, I've merged in the data sets from various government data sources. So two of them came from the Bureau of Economic Analysis, and one was county level GDP reports. So the average gross domestic product that a county reports for 2010 to 2017. The other one was county level economic profile reports, which has a bevy of about 30 different economic reports indicating such as personal income, total number of jobs, and several other indicators that are difficult to kind of group, but they represent the overall health of the county. And then lastly, the last data set I have in here is the USDA county level population, which includes births, deaths, and migrations for 2010 to 2017. The data was shaped and cleaned, and the description of this data set is that all of these are continuous variables. So this was a set of about 70 to 80 continuous variables that would be used to predict a single continuous variable. I developed some KPIs for this project. I wanted to know the total number of counties with complete housing economic data for the time period of 2010 2017. This gives you a sense of what does the scope of this data set encompass. It turns out that Zillow does not actually report housing level estimates for every single county in the United States, and that number has changed over the years. I'm interested in the lowest housing price to GDP ratio. This can be seen as kind of an economic indicator that determines productivity or just affordability for how vibrant an area is. Is it too expensive and nothing's going on, or is everybody busy and the housing market is booming? Counties, I'll be interested in counties with the greatest delta between 2017 for the following three areas, which is housing pricing, GDP growth, and population change. Again, this adds context to the report as by trying to understand what is actually going on at a national level. Be interested in industries that correspond to the highest total GDPs for counties. So, what is there one area that GDP economic activity ends up being a high correlation for overall productiveness? And then overall, the scope of this project is to develop a machine learning algorithm that can predict housing prices. And so the accuracy of those models are of importance for as a KPI. So the final data set is based on FPIS, which is a 5 or 6 digit number that is a 6-digit number that refers to a state and a county. Every county in the United States has a unique FIPS number, and there are several areas outside of the 50 contingent U.S. States that have FIPS numbers. Those were excluded from the study, and the year is also combined with the FIPS to create a unique variable. So the final data set had 21,000 unique observations and 73 continuous independent variables. This data set was split into a 25% testing and 75% training data set. Yeah, training data set. Tools used. Outside of Excel to import the CSVs and do some initial viewing, almost all of my work was done in Python using the pandas, matplotlib, seaborn, and plotly libraries. and I use this scikit-learn libraries for predictive modeling. One of my goals for this, secondary goals for this project, was to really expand my comfort and use of Python tools. So let's get right into some data visualization. This is just a split out plot of median home prices split by year. As you can see, all of the data sets for each given year are kind of similar, but they all have a very significant skew. Another initial data set visualization I did that ends up just being a disjointed rainbow is that these are the plots of every FPIS in the study with their home value plotted over time. Really, instead of looking at any individual data set, it's important to see that a lot of counties just didn't change that much. There's a couple at the top that stand out, mostly because they went from under a million to over a million. But overall, the average data set, the average county over this time frame did not change that much. This is further illustrated by looking at the next graph, which picks the home price changes with the highest actual deltas, so the highest dollar value increases and the highest dollar value decreases. So you have the top increases were all at the top of the graph, so they all started high and went higher. But what's also interesting is that if you look at the houses that lost the most value over the course of 2010 2017, every single county started above not only the mean but also the median county average of home price. So really, you have what this indicates is that you have a lot of counties throughout the nation that were just average. They just stayed very consistent and consistently low. So the biggest winners and the biggest losers really act as anomalies. For the predictive algorithms that were used for this model, there are three models chosen. Random forest, key nearest neighbor regression, and a neural network was developed. For key nearest neighbor regressions, there were two variables that were altered. One was the total number of nearest neighbors, and the other was sample weight to judge each of those neighbors. So you could either have uniform, where the nearest n number of neighbors were all given the same weight in terms of trying to create a prediction, or you could use distance, where each neighbor was judged based on how close it was to the sample that was trying to be predicted and get weighted accordingly. So it turns out that the best model that I had ended up with an R-squared value of 0.94, which is actually better than I would have expected for any of the models in this project. And that's, you're seeing the predicted versus actual in the graph on the left for the best model that was developed. So what you should expect for this graph is that it should be a pretty straight line going with a y equals x. So a slope of 1 going from bottom left up to top right. And you can kind of see that with a couple of exceptions of 1 or 2 outliers, that is kind of what you see. That wasn't, in terms of finding that model, it did search for several other parameters. It turns out that neighbor of 2 did provide the best R-squared value. Overall, uniform weights did not do as well as distance weights, which kind of makes sense. For this, you're really looking for, if you expect to have the model to have, if you expect the values in the model to have actual meaningful input into the model, weighting them by ones that are most similar should provide better accuracy. So you see that, but you also see that as you increase the number of neighbors, the overall accuracy goes down. So what is great is that the first time I did this, the neighbor of 1 had the absolute best rating, but with some refinement and especially looking at the distance factor, it did see a slight increase and then a drop down. So that is reassuring that it's not just something wrong with the model where nearest neighbor of 1 gives you the best results. For random forest regression, the main variable that was chosen for this was the maximum depth of trees for each regression tree that you could produce. And the best method is also shown here, which was at a max depth of 16 leaves, you had an R-squared value of 0.91. Again, the graph on the left shows a pretty tight distribution. Some outliers are different from what you'd see in the key nearest neighbors, but overall, it goes from bottom left to top right, which is good. Again, most of the models the models were built out. So on the left, you have the accuracy and the total number of node, or the maximum node depth that was developed. So you see that it constantly increases once you get up to max depth of 16. the model kind of stagnates and doesn't increase the R-squared value anymore. But what's more interesting and important is that the random forest model will actually give out inputs as to what's the most important variables, and I believe that should be on. It's represented in the Pareto chart on the right, but the individual variable numbers are difficult to read. It is important to note that per capita income actually represented is one of the most important splits for all of the random forest models. So this chart shows that um, the numbers on the right represent a summation. They all sum up to 1. So per capita personal income explained 40% of what was going on in the models, while arts, entertainment, recreation, and per capita dividends interest represented significantly less. But what's of interest is that of the 73 variables that were in this model, only the first 13 provided 80% um, of the normalized importance. So this model could suggest that you could get a very accurate model by just significantly reducing the number of variables all the way down to 13, which going forward would be a very, very important topic to look at. Um, what also is great to see is that I pulled in 3 data sets for this entire project, and variables from all 3 data sets are represented in the top 5 most important variables. So we don't have any data set that's sitting down at the bottom, the lower quintile of importance. So everything that we did grab has some part to play in predicting what's going on with housing prices. That's excellent news. And then finally, the last model that I developed was a neural network. This one was kind of a pain. So neural networks was done in scikit-learning. Uh, Basically, you have to give it all the information and then tell it to go try to solve it. But you have to choose the hidden layers, and the amount of hidden layers that I have, I did a grid search. So I said we're gonna do 3 hidden layers, and what's the size of each of those hidden layers? Well, let's try a whole bunch of them. So trying about 120 different grid sizes, combinations of grid sizes, ended up with a model that had an accuracy of 0.93, which is very good. It's better than the random forest. It doesn't beat out the nearest neighbors, but it is overall a good model. So like I said, with 3 hidden layers, I generated about 120 models. A good number of them ended up at 0.91 or 0.92. Only a small fraction of them ended up at 0.93. So there's a lot of models that ended up close to the accuracy of random forest, but there's also a significant number of model architectures that just uh, didn't converge at all with the limitations that I set on. And additionally, after doing the 3x3 hidden layers, I was really hoping that I could get something that would push it up to have accuracy of at least the same or better than k nearest neighbors. So I expanded the grid out to 5 hidden layers, and then did another partial grid search where I said just run and increment the grid sizes for each hidden layer. That ran for about 16 hours on my consumer grade core desktop, and I had no models that did any better. So the best model I still got was about 0.92 R-squared accuracy. Got a whole bunch that didn't converge, but this just really shows. What this really shows is that there are a lot of models that converge with okay accuracy, and an awful lot of models that just don't do anything. And there really seems to be no rhyme or reason between this model will work versus or what hidden size layers would work and what wouldn't. So in terms of usability, it's a very frustrating way to go about and build a predictive model, because it is such a black box that I have some insights as to would I choose more hidden layers than less hidden layers. It's hard to say. Um, but that was the overall result of building the neural nets. So overall, for the champion model, despite the k-nearest neighbor being the model that provided the best overall accuracy, I would say the random forest regression was the model that I would suggest that anybody who is looking at this data go ahead and use. While it's not the most accurate, it's still very fast to train, and it provides insight as to what variables are important to the models that are of high accuracy. So that would be my champion model. Now, after I completed that initial round, I expanded my scope a little bit. So this data set uses data that is from 2010 to 2017. And from a standpoint of how we think about housing prices, we don't say, well, I've got some data from 2010 and 2012. How do I predict a certain data in 2010? We're really much more interested in can we forecast with this particular model. So using the pipeline that I made, instead of splitting the data into the randomized 25 and 75% splits, I split the data into uh, segments that were to predict a year that was to be predicted, and then all of the other data. So of interest that will become a little bit more apparent here in a second. I tried to predict 2017 data by looking at 2010 to 2016 data, and I tried to predict 2010 data by looking at 2011 to 2017 data. So this is it's very much known that there'd be a lot of biases in this, and I didn't expect this model to provide high quality estimates. Um, Mainly, here's what the 2017 data housing price has looked like. So trying to predict what's going on here just based on all of the data that happened beforehand, it is a daunting challenge. But here's what we get if we were looking at to try to predict using a of uh, random forest model of 2017 data based off of 2010 2016 data. The model actually looks very similar. Instead of getting up to 0.92 accuracy, the random forest maxes out at about 0.84. And on the right-hand side, you see that, yeah, there is a little bit of a linear line, but there's a red line that represents y equals x. And what you can kind of see is that the slope is kind of skewed for the actual data set, so that overall, over the whole course of the data set, y predictions are less than actual predictions. They're pretty consistent that way. That's why it's still a linear line, but it's not laying on top of the red y equals x line. Interesting enough, if you look at trying to predict 2010 data with data that comes after it, you get a model that's roughly the same amount of accuracy, but you do have skewedness in your data where the model thinks that house prices should be more than what they actually were. So intuitively, this actually makes a lot of sense if you're accounting for if you think that your data doesn't include any kind of adjustments for inflation, which I purposely did not try to put any of those variables into the models with the initial data sets I made. So as far as future work, it would be really great to try to incorporate a way to account for incremental and systematic increases, but it's very clear that the three data sets that I added to the Zillow do not account to that on a very good degree. All right, so very quickly I'm going to touch on, there were KPIs that I had at the front, and so here's some of the answers to those. There were 2,533 unique counties that matched the criteria for having all of the data. So those 25 counties, or 2,533 counties are the counties that are represented in this data set. Additionally, a county in North Carolina had the greatest housing price delta. A county in California had a home value delta of 500,000. The county GDPs, the county that lost the greatest amount of GDP was St. John the Baptist in LA, and I think that has to do with oil and gas production, while New York actually had the largest increase. And for population delta, Cook County lost a significant number of people, or the most people over the course of the study, and Maricopa, Arizona actually gained the most people. Additionally, I had a question about affordability and GDP. So the GDP ratio that I was looking for, it turns out that Harris County, Texas, has a GDP ratio, which is GDP of all industries divided by median house price of almost 2,000. That's a very large number. While the smallest GDP ratio was Hinsdale, Colorado, as 0.176. So what's kind of interesting is how to think about this with that the home value number is included. So in Hinsdale, Colorado, the median house price is 324,000, but the GDP, there's not really that much GDP going on there. So there's not a lot of economic activity going on, but you have house prices that are still relatively high. This is a choropleth map that I made that represents affordability. So it's median wage divided by median home price. And so areas that are bright yellow indicate that an average house costs less than a year's worth of salary, median house salary, while dark colors represent the opposite. So you can see that most of the West Coast is incredibly expensive. Colorado is incredibly expensive. Unfortunately, for the goals of the study, a lot of the areas that are yellow are next to areas that have no economic data. So as a future expansion, it would be very important to figure out ways to compensate and get some more of this data for where there's sparse values missing. Um, Additionally, here's a chloropleth map of the GDP ratio of the same. So to add some stats, Harris County is at 2,000, um, while the average and the median are both in the 10 ranges. So this map actually gets a lot harder to display on a scale range, mostly because there's such variance between the min and the max. This chart just shows a little bit more of the stratification. I think that choropleth map just really doesn't do justice. There are some counties that have very high GDP to house prices ratios, while a good majority of them are rather low. Another of my questions was correlation of GDP segments to all industries, and I will start running through these rather quickly. So private industries actually correlated to GDP very high. Professional and business services GDP correlated very highly with total industry GDPs. Of interest, down at the bottom here, you had year, which is kind of expected because year really isn't a variable that should be in this, but I left it in there just to see what kind of correlation you'd see over time. You don't see any really, but agriculture, fishing, and mining actually show are very significantly decoupled from the total GDP of the county. And additionally, here's a GDP to home values. Again, professional services are up there. Governmental services are up there. So kind of the big broad industry topics are up there and they correlate very well with the total industry. But what is of interesting is variables that are not correlated end up being mining again and mining, quarrying, and natural resources. So there is a very distinct decoupling between total GDP and some of these more physical ways of producing GDP. So there's an awful lot of lessons learned for these 12 months. One of my most favorite lessons that I learned from this was that data transformation tools are very powerful if used correctly, and if you're just kind of monkeying around and not knowing what you're trying to do, you can end up doing something that takes a very long time. I had a certain transformation I needed to do that if I ran the program one way, it took 30 minutes. If I ran it another way, it took 15 seconds. The other realization that I had is it very stands out very much, I think, on the next slide, of these two graphs are the exact same data. So you've got the scale of a divergent chloropleth map matters an awful lot. So this is the change in GDP for given counties from 2010 to 2007. And on the left-hand side, you can see that the scales are set so that blue fully saturates at a GDP of $1 billion. So if your county's GDP increased by $1 billion over the course of the time frame, it's blue. If it decreased by $1 billion, it's bright red. On the left, you can see that there are several counties that have very bright red and a whole bunch that are blue. So overall, you'd say, well, it's kind of mixed. Colorado's got some interesting stuff going on, Wyoming. But if you looked at the exact same data but had different scales, so that you have saturated blue is $10 billion over the course of 7 years, and saturated red is negative $10 billion, there's only one very bright red county, and that's the St. John's the Baptist in Louisiana. But overall, you'd say, like, well, on average, the county looks like the U.S. looks like it had some cities that grew very strongly, but overall, just kind of blah, not a whole lot going on one or the other. So, same exact data set, but presented different ways makes huge differences. All right, so we touched on the conclusions that the random forest model was the predictive model I would choose as a champion. And then housing prices are heavily skewed throughout the country, and that the given data sets are good at predicting housing prices inside this data set. The predictive models were very accurate, but they should not be used for forecasting, as there is definitely bias that's missing from this data. So, future work. Uh, there's a lot of data that I wish I'm not sure if I'll have time to do in this last week of the semester, but what I think I would most like to touch on is I'd like to take a crack at trying to predict what Zillow should think that the rest of the data for 2017 for all the counties that are missing data should be. I think that actually fits pretty well within the scope of this project, but I don't know for sure what will happen with that. So I know this has been a lot of work to pack into a single presentation, but are there any questions at this time?
I'm good. Great.